Welcome to Circuit Valley. I'm Gaurav. This video is going to be fourth part in the series of video which I have been publishing recently about uses of a digital oscilloscope, in this case a really modern digital oscilloscope, in terms of decoding various buses and various protocols that are available in the embedded environment. In this particular series I have already published about SPI, I2C, UART and RS232, and this fourth video is going to be about CAN bus. You can see on your screen the setup is exactly same, and we are going to use the exact same test methodology. We are going to use a FPGA board to generate CAN messages. If you want to know more about that particular hardware, you can watch my first video that is more detailed discussed. We will be having 3 oscilloscopes from 3 different generations, 3 totally different class of oscilloscopes. On the right side you have RTB2004, 300 MHz, really modern oscilloscope from Rohde & Schwarz, has really modern intuitive software, touchscreen interface and a web interface. In the middle you have MSO 804, 8 GHz, 20 gigasample per second oscilloscope, an enterprise class of oscilloscope which you do not normally use for these kind of trivial tasks, but we will still show you what is an expensive oscilloscope is capable of. On the left side you have MDO3000, MDO3054, and that's a 500 MHz oscilloscope from Tektronix. This MDO3000 is 500 MHz and 2.5 gigasample per second. So I'll show you the setup one more time just for the confirmation. So this is our board, and you see there are 2 CAN pins, CAN high and CAN low. As you know, CAN is a differential bus. There are 2 terminals, high and low, and the difference, and what does differential bus means? That the signal amplitude is judged by how much is the difference between CAN high and CAN low. So 2 of the oscilloscope channels are probing CAN high and CAN low of each oscilloscope. Every oscilloscope is connected to same CAN bus, and we will take a look on the oscilloscope that how the signal looks. So let's get started with the RTB2004, and we will see there how does it look. So this is our oscilloscope front view looks like. I'll be overlaying the web view or web recording view of this instrument, because there you will be able to get a better contrast than the display or web view of RTB2004 is pretty active. It has a gigabit Ethernet in the back, and its frame rate is pretty much similar on the web view as well, but it's a little bit slower, but we can live with it because it's not that fast of a signal. So you can see in your screen there are 2 signals being plotted. So right now on your screen you can see both of the CAN signals, CAN high and CAN low. As I said, CAN is a differential signal, but there are always 2 signals available. The value of the signal is calculated by the difference between both CAN high and CAN low. Right now you can see on your screen the signal is quite flickering, because right now it's set for edge trigger, and normally oscilloscopes are set to edge triggers. They will try to detect the edge and try to find a good stable trigger with that. In the case of digital signal, it's mostly not possible. I'll do a signal capture, and because you must understand when I'm moving this trigger, when I'm moving this cursor, you can see these are all valid trigger conditions. There are many rising edges, and that's why you see signal is flickering. Let's zoom in a bit and we'll take a look at the CAN signal itself. So it is also a little bit hard to see, so let's first set up the trigger. As I have described in the previous videos, setting up trigger in the digital signal or in the case of buses is very easy. You just need to find out the appropriate trigger state or the bus ideal state. So in this case we will measure how much time is there between these two packets, and we will just trigger on the pulse. So you see channel 1, there is a large negative pulse of 4.66 nanoseconds, 4.66 milliseconds, and we will trigger on that. So now we know the trigger criteria. We supposed to trigger on pulse around 4.6 nanoseconds, 4.6 milliseconds, and we will find out the trigger. So we will trigger on pulse width on channel 1, and we're supposed to trigger on negative going pulse, because you see this pulse is low there and signal is low there, and we supposed to set a time. There are many possible scenarios. We want to set if the pulse is greater than around 4 milliseconds or 4.5 milliseconds, we will see a good signal there. It is as long as it's less than 4.66, it should be a good signal. So I'm letting it run. I think I mistakenly selected the other channel. That is channel number 1. Pulse is greater than 4.5 nanosecond. Yeah, trigger level is also wrong. So now our trigger is solid. and you see the CAN positive signal. I'll do a single capture. The CAN positive signal is going high, and the CAN low signal in the same time is going low. Okay, so difference between these yellow and the brown pulses is what a bus state is. So the bus state is here, suppose it's high, depending on CAN high and CAN low, and then it will be low, high, low again, and it will be low for some time. And this is how the CAN bus works. We are not here to discuss the electrical characteristics of the CAN. You must just understand that for decodation you primarily need CAN high or CAN low. Decoder can be set to decode from any of the polarity, and we normally do not care about both of the CAN signal. Normally we can ignore the other CAN signal. I'll disable the channel number 2 and let it run from channel number 1, and we will set up a decode there so that you can see a little bit better. See, there is at least 2 different packets available, because you see sometimes it flickers in the beginning. Okay, it doesn't flicker later because this is rock solid. Here it's rock solid, but you see from here up to here it does flicker a bit. So this kind of situations can be filtered out or mitigated using a bus trigger. We will try to find out if we can set up a bus trigger there, and what we can do about it. Okay, so just for the another electrical thing, I have connected the same CAN bus to my digital channels as well. It's connected to D0. I will leave the D0 on. Maybe I'll make it a little bit bigger. That's too big. But you must understand that even though digital signal is connected, you will not see anything, because you must understand the threshold. This is not a normal digital signal. If you look at it, this here is the 0. This line which is dotted is the 0, and our signal is having an offset around 2 volts offset, and it goes up to 3.58, around 4 volts. So we're supposed to set our digital buffers to sample around here, around 2.86 volts. So that's what I'm going to do now, just to show you that you can also use logic analyzer. Maximum allowed is 8 volts. So let's set 2.8 volts, enter, and you see the CAN signal as soon as I enter the normal signal. So this is how the digital signal looks, and you will see it's exactly 1-to-1 copy of the analog signal. And of course, because it's capturing the right thing with the right reference, you just need to take care when you're using a logic analyzer. Just need to make sure that your reference voltage or your level is set correctly, and then logic analyzer will also work. I'll disable it. You're supposed to set up a CAN bus, but you must also understand before setting up that we need to find out the baud rate. Okay, to find out the baud rate, as I showed you in the UART, you're supposed to measure the fastest going pulse. In this case, fastest going pulse is this little pulse, and the delta says 2 microsecond. It is around 495 kilobaud. So it's most likely it's standard CAN baud of 500 kilobaud. So I'll set up a protocol decode on CAN with 500 kilobaud. So we'll select CAN there, configure the CAN, and we can also say auto level select. This can find threshold itself, and when you press it, you see where it is finding the threshold. I think it's too high. I'll set to 2.8 volts. Okay, and it's somewhere in the middle of the signal. Predefined baud rate and 500 kilo baud rate. Okay, and this menu is closed now. Go back to the protocol, configure 2.8, 500 kilobaud, turn on the bus, 500 kilo. I turned on the bus, and let's see if it decoded. You see the data ID. I'll stop the scope for a second. Data ID BE, BE, BE. CAN has 2 IDs, I think 11 bit ID and 29 bit IDs, and this appears to be 29 bit ID packet with this data content and this CRC. Let's zoom out. We will capture one more time. So next ID is a 11 bit ID 100, and next ID is also 11 bit ID 101. So we are capturing something. Let's zoom out completely so that we can have the whole CAN packet or whole CAN frame. This is how it looks. Let's look at the bus table. This is how the CAN looks, and we have one ID packet, ID, data, and CRC. CAN has always CRC in the end, so it's supposed to detect the CRC or decode the CRC as well, and it checked status is okay, everything is fine. So now what do? We need to find out what is that odd package which disturbs us sometime. So for that, I will let the scope run, maybe capture a few packets in single mode, and I'll show you one nice feature of this oscilloscope, that you can zoom and we will analyze the signal packets which are one by one on the screen. So on the top you see this zoom window. This window shows you which packet you are looking, so you can analyze every packet one by one, and there is a marker going to be. When I selected here, you see this little pink marker. This tells you which sub packet or packet within the frame of a CAN frame you are marking at. Okay, pink marker is denoting that. So first ID here came 00BE, and let's go to the next packet. We'll see what is the ID there came. So same packet ID BE 100 101. So this is, I believe, replicating same packet which was there. Let's go to the next packet. We can scroll in our window and find out what was the packet. Same, first packet was this was the last packet, 1FF, and let's go one more time. Let's scroll down. Same BE 100 101, same packet. We still didn't found that spurious or not so repetitive packet till now. We will try to find it out. Okay, same packet BE, data content is also same, CRC is of course also same. So these all packets, they are exactly same, and you see that this oscilloscope allow you to zoom through or exactly pinpoint where the packet is. Okay, so maybe we'll trigger on this 101 or this ID or 101. I'll trigger on 101 for the sake of letting me enter less values. We still didn't find that spurious package. I'll disable the zoom, remove the bus window as well, and now I will try to set up a trigger. This time it's going to be bus trigger, not a edge trigger. It already detected the CAN, and it already also detected our bud rate and everything else, and we want to trigger on not start of the frame, not end of the frame, or not on the errors. It can also find out error itself, and we will want to trigger out identifier, and this is going to be, identifier is going to be 101 hexadecimal. Okay, and that should do it. I will let the scope run. Okay, so you see it is now triggering in the packet, and of course it is triggering on 101. So now you see that spurious packet sometime appear. Let me do a single capture and let me get lucky, or we get lucky first time. So you see this BE, they have exchanged place. This 100 and BE, they have exchanged the places. This was the packet which we were trying to capture, trying to find out, and sometimes you get lucky, as I get this time. I did one more single capture, did not found it. One more single capture, one more single capture, one more, did not find it. Okay, so this oscilloscope doesn't allow you to do quite a bit of sequential triggering. Otherwise you can trigger this condition, then this condition, or this condition after that condition. There are many kind of triggers possible, but this oscilloscope doesn't allow you, so we have to live with it. I think that's it with this oscilloscope. We decoded the package, we find out the bud rate, we looked at it, how to deal with these signals in a digital domain, and we also find out how to set up a data decode or data decode based trigger. I think that's it with the RTB2004. I'll move to my MDO3000. I'll show you there how it looks, the same stuff, how it looks there. So on your screen you can see the view of my MDO3054, and it's triggering on same channel 1, and this oscilloscope is also set for the same stuff. Let me connect the channel number 2 as well, so that you can see this is the same stuff. The same CAN bus, high and low, nothing different, and we will set up, try to capture the single and maybe do a force capture, because our trigger level is not appropriate. Where is my trigger level? We are still triggering on the bus. We are not supposed to trigger on the bus. I forgot to change it. We're supposed to trigger on the edge. And now we are set to channel number 2. We're supposed to set to channel number 1. Now we see a little bit more stable than that. Something like this. Let's look at the acquire menu. We are capturing 1 mega samples. That's okay. So now the questions come up. Same stuff we need to do. Set up a edge trigger or pulse trigger. We'll do it. Edge, pulse width positive. It's going to be negative going pulse, and it should be threshold level 2.5 volt is okay, and it should be at least 4.5 milliseconds. Okay, so same stuff we did. Set up a trigger, and you see it already captured a pretty good signal. Positive, negative is displayed exactly the same way. It's nothing different. Let's disable the channel number 2. It's not needed. And now we'll set up a bus decode. I'll enable the B1. And instead of RS232, we do CAN, and we'll do define inputs. CAN high is taken from number 1, sample point 50%. That's also perfectly fine. This is the sample point timing wise, and somehow it already configured to 500 kilobaud. It allows you to select 2 different standards, but I still don't see any activity there. Okay, so wait a second. Maybe my level is not thresholds. My level is not right. Now my level is right. Okay, let's zoom out a bit. Let's see if it can detect it. Let me do a single capture. Okay, still doesn't decode it. Define input. Is the 500 kilo? Yeah, that's 500 kilo. Okay. Bus display is okay. CAN level doesn't matter. Configure. FD standard. Define inputs. CAN type. That's what I did a mistake. I chosen the CAN type low. Okay, now we see a CAN signal. Perfectly fine. Detected. Same stuff. BE, and CRC 37EE. It is displaying in hex, and the other oscilloscope was somehow configured for the SCI. So it's a large packet. We are primarily interested in the bus table. I'll let whole packet get captured, and I'll show you the bus table. Event table, and same stuff. Started with BE and gets the 101 and everything else. We'll try to trigger with the same identifier 101, the same oscilloscope on this different oscilloscope. Menu, go to the bus trigger. This quirk bus trigger. Now it's already selected on CAN. We're supposed to do identifier. Yeah, identifier is supposed to be 1 0 1. Okay, so let it run. Let's see if it is triggering on the identifier. As easy as that. It's now triggering on the identifier, and you don't have to do anything else. So it's same stuff. Now it's triggering on identifier, and you see this oscilloscope is not capturing those signals all that often. I think I know the reason, because the memory depth is so much that you don't see that often. It's definitely coming. Package has definitely not disappeared. It's just a matter of that we are not capturing it for some reason. Bus based trigger may be slower than the edge based or pulse based trigger, so you don't see it. It appears to be a stable signal, and that's it. I think we are done with the MDO3000 as well, and I'll show you the same stuff with my MSO 804A, and get us covered with third oscilloscope as well. So it was pretty easy to decode CAN bus, and pretty easy to set a trigger based on identifier. We can set up other triggers as well. Everything can be done. Now we are looking at my MSOS 804A 8 GHz oscilloscope, and it's basically displaying the same stuff, same thing. It's right now triggering on the edge and going totally crazy, and we will set up the same stuff. We'll trigger on the pulse, and you remember we supposed to trigger on the dead time between two pulses, and its dead time appears to be around half of the period, and half of the period appears to be, we have 10 millisecond per division. So we'll set up a trigger around 4.5 milliseconds pulse width trigger. It's supposed to be positive going pulse for channel 1, and supposed to be 4.5 milliseconds, and trigger should be greater than 4.5 milliseconds. Okay, so we'll let it run. I'll disable the second channel because it's not needed. Okay, and let's set the trigger level appropriately and set it to normal. I do not see any trigger because it's not a positive going pulse, it's a negative going pulse. Negative going pulse. Now we see a solid trigger. Let's get the trigger point into the screen. So we are triggering right there, and this is our signal, and you see that flicker of the packet. This oscilloscope can also of course capture it because it's fast enough, even with the 10 megapoint memory. We'll set up a decode now. So CAN decodation, data source channel 1, type standard CAN, bitrate we need to select 500 kilobaud rate, and sample point we remember it was 50%. Enter. Signal type CAN high. We don't have any differential. This oscilloscope can trigger on differential and everything else. So we have it. We'll turn it on and see if it detects. So it does detect something. Let's zoom in and we will see if this is our packet. You remember this first packet was BEBB, and I don't know, I didn't see anything. Let me do a single capture. Okay, it's not something like that. Yeah, we see it. We see down there. Identifier BEBB 100 101 1001. This oscilloscope is more capable. It is showing you how much is the packet length, physical layer, startup frame, identifier, everything is being displayed there. You can select whatever you want to select, and it will show you exactly in the frame where are you and what is the CAN general field. So this oscilloscope is more capable. It can do a lot more things. So as it is customary, we will set up a trigger, and I'll set up a trigger on same identifier 101 protocol trigger. CAN set up this and this and this. CAN is already set up. Type standard frame, all frame, and we'll try to set up a trigger. We'll set up on standard frame identifier. We knew identifier 101 hexadecimal. I'll let it go. I'll let the trigger run, and it triggered. So let's see if it triggers on the 101 identifier. Okay, so you see that first identifier which is captures is 101, and the trigger point is right after that. So we are triggering exactly on identifier 101. Everything is wonderful. Everything is set as intended. So that's it for this quick video. I think you enjoyed it. I hope you enjoyed it. This is the fourth part in multi-part video series about the protocol decodation using oscilloscope. In the next video, we will try to cover next protocol. There are multiple videos coming about the LIN, Flex, Ethernet, MIPI, USB, and every protocol you can imagine. Even the PCI will be coming soon. So keep watching. You can visit my website www.circuitberry.com.